Good morning, everybody. Okay, so today is day 3. I will continue from where I left yesterday. Agenda for today is I will formulate a simple problem statement. As we go along, I will extend this simple one, and then I will revise the workload characterization problem because somebody said we wanted more information, so I'm just giving that again, and then present detailed step-by-step derivation of the workload so that you can see. Yesterday we defined the workload, and I gave you this framework where you can actually specify the contents or the parameters of your job and pass it to workload generation, which will model and produce a set of jobs for you, and you submit these jobs to the cloud computing, where there may be also negotiation, SLA negotiation, and then the result will be sent to you where you analyze the result and graph the output. So this is again a continuation of yesterday, as I said. Now what we want to do is to formulate problem of doing these particular things. Okay, so this problem statement has constraints and objectives. So the problem is, given P number of available processors, so P is only available processors. So the processors could be N. So out of N minus P are in use, but P of them are available. That's what I mean. Is that exactly? So we have 64. 60 is being used, 4 are available for these N jobs to be assigned to. Is that clear? Anyone? Not clear?
Clear.
Clear. Clear. Okay. So I have a set of M jobs. M is much larger than P. Okay, these jobs need to be assigned to P. The problem is allocate. Now each job also requires a certain number of processors. So let's say each one of them require PG number of processors, and we want to allocate each job, if possible, PG number of processors, such that we minimize the overall execution time of all these jobs on these P processors. But there are two subjects or constraints that the allocation must satisfy. One of the conditions is that the number of processors assigned to each job must be equal or less than the available processors. You cannot assign more than available processors to each job. That's one of the constraints. The other one is PJ cannot actually take more than the number it required, which is P max. That is the number of tasks it has, or the number of virtual machine it needs. So you can't assign more than that. This is 2. The third one is execution will only start when the job gets all the processors it requested. So under these 3 conditions, we want to allocate the available processors to the jobs such that we want to minimize the overall execution time of these jobs. That's all. This is how you formulate. If you submit your proposal, these are the kind of things like Professor Zahir wants to see. I can tell you this. So they will be happy if you formulate it this way. And easy to see it, and they will just sign it off. Okay? Now, in plain English, basically what we're saying, we assume that we have 4 jobs, job 1, job 2, job 3, and job 4. And for simplicity, assume that each job requires 3 processors. Now remember, we can't assign more than it needs, right? Maximum each job can get is 3 processors. And the service demand, the execution time of each job is 20 time units. Let's say 20 minutes, 20 hours, whatever you want. You can replace the time units. Now we have 7 available processors to run these 4 jobs. The assignment of the processor to the job must minimize the overall completion time of the jobs. Now assume only space sharing allocation. What I mean is that you can't allocate more than 1 job to 1 process. Okay, only 1 job. So now this is one possibilities of the allocation. Okay, so we have job 1, job 2, job 3, job 4. Each one of them require 3, right? One possibility is give job 1 3, job 2 3, job 3 1, and job 3 0. Now, because the constraints say that you can't start a job unless you assign all 3 processors, the last 2 jobs will wait. So you can see here along the timeline, this on top, you can see the time they completed, and on the bottom, you can see the time it started. So because they got their assignments, these 2 jobs will start immediately. And they will take, so actually the start time here, because some initialization takes place, and at time 20 they will finish. Now we have 6 more processors, right? So then after some initialization, G3 and G4 will start, and then they will finish time 40. So the overall, the total execution time is, if we assume this is 3, and we assume this part is 0, it is what? 43 time units. Now, this is only one option, one possibilities. Can you actually propose any other opportunities or any other options? Anyone?
Job 4 will take 3 3. Job 1 0, for example.
Job 1 0.
Job 2 3. Job 4 3. Job 3 4 3. Job 4 1. 0 3 3 1. For example.
Sir, assign 2 to processor each.
So we give
last one 1.
And none of them start.
So we will give first 3 processor to first one,
Okay.
and 2 to next one, next 2, then 1.
But they don't start. They only one start. So you remember here, the constraints say execution will start only when maximum number requested is assigned.
First one is starting जाएगी. After 10 minutes बाद 2 execute होंगे. लेकिन time
3 प्रोसेसर चाहिए तभी स्टार्ट होगा.
नहीं तो फर्स्ट वाले को 3 देना ना.
हाँ, दूसरे को
दूसरे को 2, दूसरे को 2.
तो फिर एक ही एग्जीक्यूट
एक
करेगा.
execute होगा तो जब वो free होगा.
See, the other possibility is just assign that 1 3 and then assign 2 2 2, 2 2 1. So 4 5. No. 3
3 2 2.
2. 2 to 1.
0, 2 to 0. Because number is second.
Yeah, so okay, that's another option, right? Assign 2 to 0 and 3 there, 1 will start. And when that finish, the other 2 will start.
Yes.
So what will be the execution time? Larger than 23. 42.
Larger than 43.
Larger than 43. So this is the
Best.
best.
If the job preemption is allowed, then we can execute these jobs in lesser time.
If the job what?
Preemption is allowed, right? Round robin scheduling.
Yeah, but one of the requirement is only space sharing allocation, which means you can only assign one job to one process. You can't actually assign time sharing.
If all the 3 processors allocated to a job are continuously working for 20 minutes or 20 seconds, whatever time it is,
Yeah,
then obviously that is the best one.
yeah.
Otherwise, if some processor are getting 3 in between after completing their job, so that processor can be assigned to some other job, so that that job also get completed during the time when other job is already in execution.
Time sharing is different scenario, but space sharing is the most in many parallel computing. Usually, space sharing is what is used mostly. But even if you use time sharing, there is context switch time that you have to take into account, and this initialization will be much bigger in that case. Okay. But I just want to give you a flavor of how you formulate a problem. And then using paper and pen, you can simply take 3 jobs and see before you code and whatever do. But one of the things that you always need to remember, these conditions, these constraints. You have a lot of constraints in real life. Okay, so the most important thing is not to formulate the problem, but look at the constraints, the subject, under which condition this allocation will be happening. You can't actually assume your own what do you call allocations. Now, okay. Now, continue with that. We have a set of jobs, and this is a set of jobs that will be executing on the system. Now, these jobs either come as a batch, where the arrival time is 0, or they have different arrival time. I will look into each one of them. So, what happened now? Number of tasks per each job. Now, each one of these jobs will have a set of m tasks, which is P max, the one I called it P max, the number of maximum tasks it can have. All right? Okay. Now, note that a task represents a part of the work. So, it is basically the job, J1 is matrix multiplication, task 1 is 1 column and 1 row. So it's part of the job itself. And interdependencies among job tasks is important. So what interdependencies I mean is that when this task finishes its execution, it may send to another task to continue, or it may wait for the data to come and, before it starts. That interdependency you need to take into account. Now, a job is said to be small or large. Now, if it consists of a small or large number of tasks, I will talk about this. Tasks with a large service demand may introduce large queuing delays, because if you put big task or big job in the system, then it may wait long time, or any tasks that come after it may wait long time. So that is why we now divide jobs into small and large. So this is a small job, okay? This is large job. And so as you can see, based on the analysis, this is not actually randomly classified. It is based on the analysis of real workload, logs, and traces. We can actually now know the percentage of small jobs with a small number of tasks is higher than large jobs with large number of tasks. So the majority of jobs are basically small jobs, and only few jobs are very large jobs. So for this reason, we examine the following distribution for the number of tasks. Tasks with a large service demand may introduce, again, I already said this. So every job will be described by these attributes, okay? Every job. Service demand, arrival time, and number of tasks. Now, a job doesn't have to have a number of tasks. It can be one task. The whole job can be one task. In this case, we say the job is a sequential job. But if it has multiple tasks, it is divisible, then we can say it is can be executed parallelly. Now, if your job can execute parallelly, in parallel, the tasks, then if you actually put it on a number of processors, then they speed up, they scale, it scales, right? It's fast. So if a job takes 20 minutes, and you give it to 2 jobs, that cuts what? Half, right? 2 processors. So one will take 10 minutes, one will take also 10 minutes. At the same time, they finish in 10 minutes. So 50% saving. That is what this shows. But in reality, that is not correct, because there are some overheads. Every time you split your job into 2 and assign it to processors, there is some overheads that you need to take into account. Today we will create 4 tasks, and we will look at them, each one of them. But what this shows is that for work 1, just a look at it. So work 1 actually scales, workload 1 actually scales much better, and followed by work 2. So work 3 is the poorest one. Now we can actually combine this all together and get work 4, which may be somewhere either here, here, depending on what we use. So I'll show you how we actually get this one also. Remember this formula? So a lot of people had, a lot of you had some problems yesterday. I am going to revisit it. Basically, this formula has 2 components. One component is the overhead, and the other one is scale up. The graph I just showed you, that's the scale up, because if you see, this is, if a service demand of a job is 20 and you give it to 2, that is what? Cut by 50%. So the more you give it, the more it speeds up. But this controls that speed up, this parameter here, because of some overheads that is associated every time you increase the number of processors. Now, you see these parameters, this one, these 4 parameters are here. By changing the value of these parameters, you can actually create a number of different workloads, just changing 4 parameters. Okay? Is that clear so far? Okay. Now, there is certain level of load imbalances, as I said, because when you actually, if you look at the example I showed you here, you see here, even though you assign this job, it can't start. So even if you parallelize your job, because of some issues, there is some imbalances that can occur. That is what this parameter actually handles. Okay, and P represents the degree to which the work is not evenly spread across the P processors. That is load imbalance. That is what this particular parameter accounts for. And we know that this parameter is always 1.1, between 1.1 and 1.2, always in real environment. So we can assume it is 1. Always it's 1.
So is it empirical finding?
Empirical. Yeah. From traces, from the logs, they found that it is always between 1.1 and 1.2, never exceeds. Which means we can simply say it's 1 without losing any or having any impact. The lambda is part of the overall overhead, right? And it increases the work per processors due to parallelization. So sometimes the processor can wait for data or can actually be suspended, like the one we saw, because there is no enough processors there. Now this actually accounts for the communication delays. And sometimes the network can get congested. So this also introduces another level of delays. Okay? Is that clear so far? Okay. Basically, if you increase the number of processors, this also increases. But regardless of the increases, these three values, this one, and that one, will always be smaller than this, unless it is what? See, if it is interreactive job, 0.1, right? So you don't even get these ones, right? Because you just send it and immediately comes back. But if it's only you have multiple processors and big jobs, it makes sense. Is that okay? Okay. Now, let us create the workloads that I said we're going to create. Now, W in the runtime function represents total service demand of the job. What this means is the cumulative. See, I have J1, J2, Jn, right? The cumulative job service demand is W. And each of the jobs will have their own service demand. Okay. And also you remember the two jobs, we classify jobs either big or small. Now, the small jobs will always have the average service demand is 1.3. Now we know that one fourth of the jobs are big ones. 3/4 of the jobs are small ones. So that means almost 80% of the jobs are small ones, 20% of the jobs are big ones. And the average service demand that small jobs request is 1.3 time units. Whereas the large jobs, which make up 1/8, it is 101. The service demand, the average service demand is 101 time units. This could be thousands of seconds. Okay, now you understand 101 and 103. Okay, now the job here this one is the mean value is always 13.76. That is the mean, the average of all jobs. Is that okay so far? Okay, good. Yesterday I talked about the coefficient of variation also. So what this basically means is that if we increase the variation, the workload variation, how much the allocation is affected, how sensitive the allocation is. So you have the allocation, the scheduler. The scheduler is sensitive to many things. One of it is the coefficient of variation of the workload. So if you vary the coefficient of variation, then it may have some impact. So when we want to study the sensitivity of the scheduler, we actually vary the coefficient of variation. I gave you that. If you don't remember it, yesterday I'll dig it out and see if we can see it. Now, if that coefficient of variation must be always either 1 or greater than 1. So if it is 1, you have exponential distribution. If it is greater 1, you have two-stage hyper exponential. Okay, so that's why here I said 3.5 or 10 or whatever. Okay? Now, remember the workload speed that we talked? The speed up, this is the formula that we use. It looks very complicated. There are only 3 parameters. One is the number of processors that each job asks, right? Pmax. And the number of processors in the system, the whole system. And this value determines how interdependent the tasks are. Remember the matrix multiplication? They're basically not dependent, right? You can throw them everywhere. So that's why we have infinity, which is 0. So there is no dependency. With 2, the smaller this value, the more dependency is. Now, all you have to do to see how these guys are faring in terms of scalability, you only need to put in this and the number of jobs, the number of processors they ask, or the number of tasks they have, and this value, that's it. So if you look at this here, I have, as an example, I want to create work 3. Work 3 is 0.2, so mu is 0.2. Now I can vary the number of tasks this particular job wants, right? If it's one processor, then we know it is sequential. It's 1, 2, 3, 4. What I can vary to study it is scalability. So what I did is that I just looked for 4 processors. That's what it needs. And our system has 32 processors. Now, if you actually calculate this, you will get what? 1 value. And this for one processor, for one level of processors. If you put 1, then if you put 4, then if you put 6, then if you put 9, you will get 4 values. Right? Then you can actually now graph what? The speed up against the number of processors you assigned. Is that clear? This is exactly what I did here.
So this is for the setup of SMPs, isn't it?
Yes.
This is not for distributed systems.
It is
only
for
SMPs.
It is for distributed systems, for cluster computing.
Okay, but actually the communication cost is nowhere coming into picture.
I purposely left it because yesterday I tried to explain, and the more I push in the parameters, the more it became complicated before I even got to more complicated areas. I purposely left it out. Remember I gave you a formula yesterday for communication, how to calculate? Okay, so I would stay away from it until everybody is comfortable, or at least majority of you comfortable. Okay? See this speed up that we calculated, this is the number of processors we assigned to it. That is how, yesterday you asked me this question, right?
So how is the value of mu is being calculated here?
The value of mu is actually given to you, because the smaller it is, the less the speed up is. So if there is 0 or infinity, that means there is no actually, it is just bag of tasks. Scalability will be up. There is no overheads that much. But these ones, which Professor Zahir asked now, implicitly, this formula implicitly has it. But we can also, oh, I'm going down. See, this formula had, this is actually captures the communication and congestion delays. Okay, so implicitly it is in there, but we will look at more explicitly later.
Maybe I think, sir, we can take mu as the serial component in the job, maybe.
Yes, yes, you can. But it is basically, it was empirically shown, but we know that the smaller mu, the more your job is not scalable. Okay, so which means a lot of overheads, whether it's the communication or the structure of the workload itself. There is a lot of factors in there, but we just minimize it to say it is when u equal to 0.2, 0.1, like this. Okay. So are we okay so far? Following? Any questions?
Shouldn't we take it 0 instead of infinite?
This is how everybody represent it.
A bit confusing when we are saying that the higher value is making different aspects.
Yeah, the higher the value, the more scalability. But every one of us use infinity. I don't know. What are we doing? Plus or minus infinity. So you can put 0 if you want to in there. Okay. I'm just putting in, if you read, I gave you a number of references to read. If you read those references, you will see infinity also. So you don't come back and say, to me, you put 0 there, the paper says infinity. Okay? Now, if we actually look at if you compare this here, and if you now increase the processors to 60, the scalability of workload 1 increases much more. If you see here, it was about 2. Now it is actually increased to about 8. So manifold increment, scalability. So why is this? Anyone? There is no overhead, right? Much overhead, because it is bag of tasks. The only thing they need is runtime, processor. They don't need anything else. What about this one? It's about 1 point, almost 1.5 or 6, right? See, it did not actually increase that much. So from 4. how scalable is your workload?
फार्मूला ड्राइव किस लिए किया तभी समझ में आएगा सही पूरा ड्राइव फार्मूला न्यू तो स्केलेबिलिटी है वो तो कई सारे फैक्टर्स पर डिपेंड जाएगी ना जैसे सर ने बोला था पहले कि न्यू इज डिपेंडेंसी अमंग द टास्क तो आपको स्केलेबिलिटी फैक्टर बोल रहे हो स्केलेबिलिटी फैक्टर तो कई सारी चीज़ों पर डिपेंड करेगा डिपेंडेंसी इन्फिनिटी हो गई डिपेंडेंसी कम होगी तो हमारा स्केलेबल ज़्यादा होना चाहिए
ये वैल्यू इन्फिनिटी होगी तो ये बैग ऑफ टास्क इंडिपेंडेंट टास्क अगर इसकी वैल्यू 0 के आसपास है यहाँ पे डिपेंडेंसी टास्क के बाद
डिपेंडेंसी मैं कह रहा हूँ न्यू की वैल्यू इन्फिनिटी हो रही है यानी कि बढ़ गई तो तो ये गलत है ना ये डिपेंडेंसी तो बढ़ गई तो बैग ऑफ टास्क में तो डिपेंडेंसी बहुत कम हो चुकी है ना इंटरडिपेंडेंट हो जाए
ये मतलब जब न्यू की वैल्यू हो जाती है तो वो टास्क इंडिपेंडेंट हो जाता है मतलब वो सिक्वेंशियल तरह मतलब वो किसी
तो न्यू इंटरडिपेंडेंसी होनी चाहिए सॉरी वो इंडिपेंडेंसी डिपेंडेंसी होगी तो उल्टा
हाँ तो
इंडिपेंडेंसी होगी ना
Okay, we did. If we see, if we look at scalability, it is almost is very small, right? And the more you increase, the less it gets. But it doesn't have any impact on bag of tasks. So scalability is only impact, application only gets impact if it has some interdependencies. So you can see this is what we are trying to say. Okay.
And this it means it should be infinity, not 0.
Which one?
Infinity means whenever it's scalability factor, whenever it's big, then speed will be higher. Then it should be infinity, not 0.
Somebody
it's not over
said 0, so
it's scalability factor. Then whenever it's big, speed up will be higher.
we use infinity, so you can actually put any number in there and check it yourself. It's just, I gave you the formula to see how scalable a workload is. You can see the scalability of your workload. When you create, you can see it. You put any number in there. Okay?
0
all right. Now, for this kind of job, which is very scalable, that I just showed you, it has very good speed up, and because the mu is infinity, and an example is matrix multiplication. The number of tasks that you can break this is computed by using W over and so you have to take the upper bound because this can result in fraction. So you can do down or up, but usually we actually use the upper one. So this one actually takes into account the congestion and communication delays. Now remember, hyper-exponential, two-stage hyper-exponential for service demand. Now, I divided the job into large and small, right? So this part is the small jobs. This part is the big jobs. Okay? So remember this number, where I got from? I told you already earlier. And this is for a small number, small jobs, 1.3. And you also remember the mean value of W, right? 13.76. And if you actually divide 13.76 101, you will actually now this is 0.125. Okay. If you put in there this 0.15 for big jobs, and whatever value you get from here is very small. Is unless really this is 0, then this makes sense. If you divide 13.76.13, this is much bigger number than 13.76 divided by 101. What this basically says is that most of the jobs will be small ones. So this is how the service demand is calculated. A very easy one. Is that clear? Any question? Okay. Now we looked at the scalability, the formulation, how we formulate the problem statement for job allocations. We looked at scalability of jobs, workloads that we create, and we looked at how we compute the service demand for it. Now, okay, this is an example of workload 2, where you can actually see that the mu is 0.4. So this affects scalability, right? So there is a lot of overhead. And that is why you see when you see this is the job I'm talking about now. So it's not bag of tasks, but it is actually interdependencies are there. So that is why you can see here. And this kind of applications is example of n-body simulation or plenary movements applications in scientific applications. And again, the same formula to calculate the number of n's in here. Now, I only showed you one part of it, but actually it repeats. This pattern repeats many times. Okay, so for just this, the first iteration, you can actually calculate the number of tasks, and then second iteration changes and keep changes until the final result comes. It's very long job. It's not actually a small job. The third one, which is very difficult, the scalability is bad, 0.2. Okay? Now, the fourth one, which I said here, this one is actually a combination of these three. You can combine them by simply changing the 4 parameters I showed you. Just change 1, 2, 3, you get the combination of these jobs. Okay? Okay. Now, let us look at the arrival time. Before I look at that, we will look at this particular system load, and then we have 10-minute break and come back, okay? Now, we want actually, before we run a job, before we submit, before we allocate processors on the job, remember the system is always running some jobs. There are some nodes available, and there are some requests waiting to be assigned. So we always want to make sure what is the load on the system right now, and before we make the allocations. This is what is basically this says. This one on the top one is if I give a job one node, if it executes sequentially, this is how much time it takes. E t to the power t, one means one processor is allocated to this. In a system of n processors. And T stands for the inter-arrival, the mean inter-arrival time of the jobs. How often they come to the system. So I can actually use this to compute the load on the system at certain time. So if I wanted to know in the next half an hour, what will be my system load look like? I can actually predict by simply using this formula. And then I can make the appropriate allocation without violating service level agreement. Okay?
So this load is being calculated for each processor?
For not each processor, each application you can look at it. So we have all processors here in the system. And this is if I allocate to this job one processor, this is how long it's going to take. Okay? So assuming there is only one processor available, I can allocate to this, and this job can run on sequentially on this job. And basically what this will give you is what? The time that an application will take to run on one processor, and if you divide that by the number of processors and how often the other jobs will come, then you can see, you can get the load on the system. That's all you can get. What will follow from this is I want to actually calculate the utilization of the system. But to calculate the utilization of the system and to calculate the arrival and inter-arrival times, you need to know actually, you have to have some idea about the load on the system.
So that way in the numerator you have the sequential time.
This is sequential time, but this is actually
So you are just estimating that if it is on n machines, what will be the average time, the average loop?
I'm looking for the average here. Okay? Because I'm just estimating at this moment.
And this is for homogeneous processors.
This is for homogeneous processors. It's not all the processors actually have the same environment, the same execution, the same CPU, and the same thing. Okay?
But then the problem will become complex if you consider the heterogeneous virtual machines.
Of course, but the problem is now, because everything is virtualized, these virtual machines can run on any systems, but still there is heterogeneity. It now sort of what happened is it is now heterogeneity is taking the back seat. People are not talking about it because of the virtualization. There is heterogeneity still. Okay. One of the problems with heterogeneity is not only running, but also a different running time, but it also it may not even run at all. If the systems are different, you program. One of the problems we had with clusters and grid computing was a lot of failures because the whole environment is different. The CPU is different. You design for 64 programs to run, and they have 32. It doesn't work. But now, because everything is virtualized, and as a user, you don't have to worry about it. The system will take care of it. That's why I did not actually introduce in here about heterogeneity. But heterogeneity is there. Okay?
But even now, this Google and Amazon, they provide virtual CPU.
Yeah.
All homogeneous, I consider. Heterogeneity is there, but when they provide, they will say in terms of vCPU.
Yeah.
Virtual CPU, and all virtual CPU same.
Yeah. Okay. These are the workloads I just told you about. Okay. So if you want to read on everything that I just showed you today, you can find it in this paper. Okay. I will actually put it with the slide, and they will send it to you. Okay? We'll take 10 minutes break and come back. Now we will finish with the inter-arrival time of calculating this inter-arrival time for the jobs. Now, here are how the jobs can come. Okay, so they don't actually come one after another. These are the 4 jobs that we looked at today, and these are the values. You can simply substitute these values. This is the exponential function that we talked about for capturing the inter-arrival time, and lambda is given us equal to the runtime of a job on one processor, and this as Professor Deakin said, it is actually the average by runtime on one, and then divided by load, and n. N is the number of processors in the system. So we can use this to compute the value of lambda and plug it in here, and compute the inter-arrival time. Now, I showed you the formula for calculating the load, remember? And I was trying to recover it. I deleted it by mistake. A bunch of slides, I don't know how they disappeared. So it's not there anymore. But you remember the formula, right? I will type it again. But I will type it again. I'll give it to you before the end of the day, the formula. Or you can actually see the paper I gave you. I said, look at it. It's in my paper. It's there already. Okay, so we can calculate the execution time on one processor. We can do this because we know this, the mean service demand for all jobs, which is 13 point something. What was it? 13.76. We know that by using the theorem of total expectation, and based on the number of tasks in your application, in one particular application, we can actually derive the value of this one as 0.30, and all this is done in there. And also the value of this can be given like this. For the workload, that is highly scalable, it's 0. For a workload that is okay, but it's not as good as this one, it's 2.0. And for job that's fully scalable, it's 5. The mix in between here is some value between the maximum. If you mix these 3 jobs, you remember job number 4, we actually created by mixing the first 3. So the value will always be somewhere between the minimum and the maximum. Okay? So we can actually do this and plug it in here and compute the value of T1 to actually get this.
So mu can be calculated by some mean, or it is just a loss on the basis of that only it is value of mu.
Yeah.
That infinity 0.2, 0.4
Yeah.
can be calculated by some mean, by seeing the graph of the job or something like that, or it is?
That's how actually they drive. For the first 3, it is empirically driven. For this one is because you're mixing a number of jobs, you can actually decide in between these jobs. Okay? Because whatever you mix, this one, it doesn't really affect, right? It's 0. So the impact on this job will come from these 2. So the value has to be between these 2. That's what we say. So now I calculate this, right, using all this. Somebody asked me to put the numbers in it. I was trying to put the numbers in it. Something happened and it just disappeared, the slides. So I can actually calculate lambda from this, right? I already calculated all this here. So I know the number of processors in my system, 32. So far we were working on 32, right? And I know the value of this from this. And so I know the load from the other formula. So you plug this in and you get your lambda. You can easily calculate lambda, right? And then you can calculate, instead of x, put t in there, you can calculate the value of t in there. That is how we actually calculate, present the inter-arrival time. And if I show you the paper, see here, this is exactly how we calculate the inter-arrival time.
1997.
So inter-arrival time t is calculated by using the exponential function, and this is the value 1 over lambda is equal to the execution time on one processor and the number of processors multiplied by load. And load, I already gave you the formula, and you can see that for the workload that is very scalable, you will find that this is 0, the execution time. If you follow the formula that I gave you just now, you will find this to be 14.06. And for the second one, you will find 16, and the third one, you will find 19.06. For the workload number 4, which is between these two, as I said, you will find with this value 2.34, it will come to 16.4. Just put the numbers in there. This one will come automatically. Okay? So that is how I actually calculate the inter-arrival time of the jobs. Each job will be simply, you can calculate the value. Once you get the value, you say, this is the arrival time of this job. And then the next job will arrive after you calculate the inter-arrival time. As soon as that time comes, then it will come, another job will arrive. So this is the formula I used for the inter-arrival time. This is what I actually derive by using the formula I just showed you. This one, you remember this one, right? How to calculate these two values. And this speed up is what I just told you earlier, and put the numeric values in it and calculate it. And let's look at some okay. I don't think you can see that. So if you see, this is for workload 1, okay? And can you see it? No? This is actually taking into account heterogeneous and homogeneous systems. The het R stands for the processors are heterogeneous. So they don't actually, their speed is different. Whereas these ones are the homogeneous one. And you can see that the AHS is the algorithm I proposed. SST is the algorithm I believe it was proposed by a professor who passed away in Toronto University in Canada. And you can see that for homogeneous systems, the algorithm I proposed is a bit better, but as the number, this is actually looking at the impact of service demand, coefficient of variation I told you this morning, if you remember. So I'm actually looking at the sensitivity of this job, workload 1. I will look at the actual running time before this. But you can see that the impact of heterogeneity on the system. If the system is heterogeneous, there is a much cost to actually run on it. The reason is because the task you actually schedule on the heterogeneous node will wait longer, and then it impacts the overall job execution time. That's why you see the gap between here and there is very big. Again, this simply shows you the impact on service demand or coefficient of variation. Again, somebody asked me yesterday, in fact, this job, we looked into what is called I/O factor. Some of the jobs are read, 50% read. You know, they have I/O impact in there. It's not only CPU. It is they are jobs that do I/Os. Now, if you look at this diagram, again, for both heterogeneous and homogeneous systems, this is the load. Remember the load formula that I showed you? This is the utilization of the system. And here is the mean response time, the average response time for 10,000 jobs at a given time. Now, as you can see, that when we vary the utilization of the system, the two policies under homogeneous is basically very similar until the utilization starts increasing. As the utilization starts increasing, they start separating. But for heterogeneous systems, you can see they actually start separating around when the load is 3, where the AHS, which I proposed, basically remains somewhat stable. The other one actually goes very, very deep in terms of it slowed down. It takes a lot of time to complete the jobs. The algorithm I proposed is not that much sensitive to the heterogeneity of the system compared to this one, which is actually used by a system called load balancing system, which was a big company. It was developed in Toronto University and became, during that time, very big, because that is when we start using cluster computing, multiple clusters in different places. That gave a way to what is now called cloud computing. And this is what actually was used in that algorithm.
How do you increase the utilization experimentally?
No,
by adding more load, or what?
Yeah, by adding more load. So you increase, instead of running, say for example, the system is, I think this one is 64. If you have 32 nodes and you add a larger number of jobs that keep the system at certain level, and then you throw a lot of small ones that actually grab the rest of, so you end up with only few nodes being released, but you can keep that consistent because large jobs will hold the processors. If you want to get up to 0.3%, you load the system with large jobs that will hold this, that it will execute on the system. And then you put the small ones to use the rest of the processes. Is that clear? No? Okay, so I want to keep this utilization at 30%. Okay? So let's say I have 30%. What this says is basically 30% of the 64 processors will be busy. Okay, so what I'm going to do is I will throw in large jobs, not small ones. You can do with small ones also. So large jobs will hold, say, I want to run an experiment for 3 hours. During these 3 hours, these large jobs will run for 4 hours or for 5 hours. They will give me consistent, while my experiment is finished, consistent level of load. Is that clear? No? Still? No? Can anybody say yes or no?
Yes, sir.
Yes. Yeah, so that is how we do it actually. We keep the system loaded. But in experiment also, you don't do that. In experiment, you can vary the load. Okay?
Why didn't you plot the graph between load and mean response time rather than utilization?
I did actually, because the journals, they ask you 10 pages, maximum 10 pages. You put the rest on my web page. You can find if it's still there. But now from 10 pages they went to 8 pages. So it is going to be very, very difficult for young researchers. You can't publish in IEEE now in more than 8, sometimes 12 pages. Few journals in there is 12 pages, but most of them is 8 pages. And some good ones now, they ask you for 6. So we did a lot of experiment, but you can only publish part of the experiments. Okay, that's why I'm showing you just utilization. But if you look at other part, when you get to look at it, you can also see we have done many other experiments. Now here, you remember workload 2, it's not as scalable as workload 1. And this workload has some communication impact. I/O comes into picture here. Again, for heterogeneous systems, they probably track each other, is about maybe 10% improvement. But in terms of heterogeneity, you can see again the gap is very, very high. As the load increases, the other allocation mechanism really suffers a lot. Whereas our algorithm basically is sensitive to these kinds of problems. Now we looked at I/O. Where is it? I think I simply explained the I/O factor. Now, I described this, but I want to describe this for service demand. Remember the way we calculated each job's service demand by using two-stage hyperexponential. And remember when I said we use coefficient of variations to see the impact when you vary the two-stage. Remember it forks like this, lambda 1 and lambda 2. It forks actually based on coefficient of variations. Now, if you vary little bit any one of these value, the workload you get varies also very greatly. So what we did here is we simply vary that coefficient of variation to see how sensitive it is. Little change, it will change. So you see the one we proposed is not that much sensitive as compared to the other one. For all workloads, actually, it's not only workload 1 or workload 2. All 4 workloads that we looked at, it's not sensitive. Now, this looks at coefficient of variation for arrival time. The arrival time exponential function, exponential distribution gives you a nice inter-arrival time. You can disturb that by using coefficient of variation of arrival time. So you can speed it up. It gives you really, if you don't do variation, you get a nice arrival of these jobs in a certain predictable manner. Now, if you use coefficient of variation and vary that means basically vary it, it actually may send a lot of it, may send nothing, may send, shorten the times, and so it disturbs the arrival time. Now, if these arrival times are disturbed, what do you get? How is it impacted? This is real life. In real life, sometimes you get, say for example, a machine that prints checks for employees. During the end of the month, it becomes very busy. right? And then during the other weeks, it may simply do something simple. That is what we try to show you here. The arrival time can vary. It's not constant, or it's not really very nice patterns. So if you change the pattern, what do you get? This is what you will see. The pattern, the changes will actually have impact, but more so on the other algorithm that is proposed by the group of Savage, actually, sorry. This is for workload 1. Okay, now what I want to show you is just one by one. So far, we simply run the application without any background job. So there is all 64 nodes are dedicated to the parallel jobs that come in. Now we want to see if we actually now have some background workloads. So the company sends these high priority jobs that will run in the background. How these in the background running jobs affect the parallel jobs? They do affect, right? They now share the system with the processors. Somebody talked about time sharing. That's what we're actually doing here now. We are time share between background. So the background job is actually wakes up and uses only a little bit and then go back and run and come back and run, come back. So you can see that when we see the mean response time of the jobs, you see as the load increases, the algorithm that we proposed, AHS, is nicely also increases. Whereas the other algorithm, this one is actually goes out of whack, and the other two actually works much better. So this is for two, under the heterogeneous system and under the homogeneous system. And you can see that under heterogeneous system, the one they proposed is greatly affected by background workload.
So in this experiment, you have mix of both background and foreground.
Foreground, yeah. Yeah.
And how often you execute the foreground job and how often the background?
We simply run, let the background job share the CPU. We run the foreground job in one CPU and then randomly send the background job. Then this background job will come and share depending on the local CPU, the local scheduler of the CPU, they schedule and run. We didn't control that part. We simply said, here is the background job, this can run with the foreground job.
And both have equal priority?
Both have equal priority, yeah. In fact, I don't know if it is in this paper, when you read, look at it. In fact, I have done a couple of papers on when the background job has higher priority than the foreground job. Because the background jobs probably, the foreground jobs probably can be sent to public cloud, and the background jobs, which are sensitive jobs, can run in local jobs. Therefore, assuming that the foreground jobs can go out, we then change the priority, saying the foreground will have higher priority, but it doesn't actually evict the foreground job. What it does is it shares, if the foreground job runs 2 times, the background job will run 1 time. So we lowered the execution time of the foreground job. We still, it's still, what I want to say, it still gets to the finish line, but slowly. So yes, I did some work like that. I don't know if it is here or somewhere. You can look at that. Now, the I/O factor. So 50% of the jobs will be I/O intensive. There are 50% of the jobs are not I/O intensive. In this case, we run this experiment for two environments, homogeneous and heterogeneous. You can see that still in heterogeneous systems, it tracks well as the I/O factor increases. Now, here we're saying that 90% of the I/O factor, the workload is I/O. So up to here, you can see up to 50%, they tend to work very closely. They tend to produce very close results. But as the number of I/O workloads, I/O intensive workloads increase, the two algorithms start separating. Okay, so there is impact. If you compare the jobs earlier, the graph I showed you, without I/O, it is higher. The I/O actually takes much more time here. If you look at the response time, the I/O response time is very high because the jobs actually wait most of the time. As you can see, it is up to 800 units of time is slow, where the other ones is in the neighborhood of 100, 150 without I/O. When you include I/O, the whole response time actually goes down. Now, this is for workload 1, that is very good scalability. Again, you see for workload 2, with good scalability, but not as good as workload 1, the timing increases from 800 about 1,000. But you can see again, for heterogeneous environment, the two policies start separating. Around 20% of the workload has I/O. And you see the way it tracks. And under heterogeneous environment, the other algorithm takes longer to produce result than the algorithm we proposed. Well, I think that's all the experiments that I showed you. The formulas I gave you, everything is in that paper, everything you want. I hope a lot of questions yesterday you have is much more clarified today. Okay, this is basically how I did the experiments, used those all that I told you. The workload is generated exactly the same way I told you. Where is anyway? You can find everything I told you today. This is, you remember yesterday I gave you this. The communication is exactly the same thing. What I showed you. This is the startup. Before you start the communication, there is a startup cost. And then the size of the message that you're sending divided by the bandwidth of the network. That will give you the communication cost of each message. Each time you send a packet or a message, we compute this. This is how I generate the background load. You can see here. And so forth. It is easily readable than the paper I gave you yesterday. This one is much easily readable.
So is this experimentation part done on some simulator?
For this paper, no. For this paper. For the other paper, yes.
Okay.
The paper I gave you yesterday. Remember yesterday yeah, so that one is actually done on simulation. So, are we ready this afternoon to do this on cloud? See?
Yeah.
Yes.
There is application there already. You saw that example, right? But that example is only for the batch. It's just coming. The cloudlets are simply coming at the same time. What we want to do is to make it real. Just change the time using exponential time that I showed you today. That will make it the pattern of arrival. The jobs will arrive not as batch jobs, but one after another. Okay, and then in the cloudlet, the example that is given there, the time is already, if you see the object, it says the time is equal to, the service time is equal to some number in there. Instead, we actually want to generate that time using two-stage hyper-exponential time. And then we run in the cloud just by making these two changes. You can compare the batch and when the jobs arrive at different time and have different service demand. What you see now in there, the other day when we looked at, all the jobs have the same time, all the jobs arrive at the same time, and they simply give you a nice answer. That is not reality, so we wanted to actually do exactly what we did here. Okay? Then, if we have time today, or if we don't have time, we can continue this. We can use the 4 parameters I discussed today to create different types of jobs. The example you see on Cloudlet now is W1, what I showed you, bag of tasks. It's not actually, there is nothing restrictions on it. So we can actually change them now this afternoon or tomorrow to make it actually different types of workload and see how the results will be affected. Okay? Okay, do you have any questions? I'm happy to answer. Any questions? No? How many of you is writing proposal? PhD proposal. A couple of you already asked me about it or told me about it. I'm just saying I'm going to help you if you have any questions on it. Yeah, okay. How many of you are writing papers? Okay, so if you are interested...
How many of you are writing research papers?
Oh, you see, now you say, going to say, everybody say.
Because you see that you can get some tips also, na?
Yes,
sir.
I'm happy.
And research proposal, PhD research proposals? Only one is right. Now you are also writing, research PhD synopsis, etc.
Yeah.
Right?
So I'm happy to help on that also.
So what are the topics on which you are writing? Scheduling. Of?
Cloud scheduling.
Cloud scheduling.
He's working on service level agreement.
Oh, SLA.
SLA.
That's it.
I have written 2 or 3 papers recently. You've seen them, right?
Yes.
On service level agreement and negotiation.
VM allocation and migration.
Yeah. Yesterday we talked about migration, you remember? So we will continue, in fact, increasing, and I will show you one of my papers where we did a lot of, that paper is actually cited more than 1,500 times, 1,500 times on the migration actually.
In the position of the editor and this one.
Probably we can use heuristics and meta-heuristics also.
I will talk about that. I will introduce heuristics and meta-heuristics.
And meta-heuristics.
Yeah. In fact,
evolutionary. These all are meta-heuristics.
Yeah, these are meta-heuristic. All we will talk about them.
Some questions
online scheduling.
This one.
Yes. Yes. We have used it. Okay, so for the way I did it, I don't know if you were here last year. Was it last year when I presented? Okay, so I actually presented an algorithm that will use it to determine the level of energy that you need before you allocate any jobs. You can determine energy usage and sell that energy. It's not actually now nobody sells energy, but many countries start actually selling energy now or charging for energy. So we can actually do also that in cloud computing. It won't be too long before they can do it. Now, a lot of times, he's right, these algorithms are actually used in offline environment. Okay? But when you have systems like cloud, you can actually do this very fast.
I think what probably the question is that, see, the meta-heuristics are often applied not only for static systems because it takes some time and some instances of the data so that it can work upon that and can generate some schedule for that. So probably the question is if it is dynamic stream is coming of the workload, etc., then how it will be feasible to apply it?
No, you apply that for planning. So you can plan for just planning. See, there is, at the planning stage, we have many things. Sometimes, if you look at, what do we call it? The name will come to me, but basically I'll explain it to you. Yesterday I talked about this briefly. The airlines, they actually double schedule, double book you. Okay, they double book you, and then if the flight is full, they will give you 2 choices. One, free ticket, or they pump you to business class. If you can't, you will actually be, you get hotel and then you get maybe free ticket to go somewhere. And then they will fly you tomorrow. So I applied that idea, the meta-heuristics on this idea. So it is just planning for planning purposes. You can do this. If I do this, what will I get? What will be the outcome? So if somebody is coming and saying, I need my execution right now, and I'm ready to pay premium, okay? So I can actually, because I already planned, using meta-heuristics, I can actually see which of these jobs I can kick out.
Idea is good.
Yeah, so yesterday I talked briefly. You can do that. You can actually plan the same idea that now doctors start using. They will book patients, and because you are in need, if you go to a doctor, they will make you wait there for as long as they want. So, but the airline actually gives you a better intuition of using meta-heuristics. We use it to plan. There are people actually now in Sydney University. I don't know if you've heard Albert Zumaya.
Yeah,
they are
very
yeah,
famous.
yeah. So his group is actually working in this area now. So they do work. They do apply. It is possible to apply it.
He has applied a huge lot of meta-heuristics on various kind of problems, not only in cloud computing, in mobile computing also.
Yeah.
What is the use of DBFS enabled processor in data centers, cloud data centers?
So again, come again.
DBFS enabled processor.
Okay. So yeah, it's basically.
The jobs are independent. Type of task. Reducing the frequencies.
No.
Do they have some dependencies?
No. What you do is that if you have 1,000 tasks running on 1,000 job resources, they take 1,000 units of energy. So what they're doing is that they either lower down the energy consumption on the CPUs by lowering down the processing speed, or they consolidate all those jobs onto, say, instead of 1,000 to 40, 50
But the
jobs.
time is increasing. If we are reducing the speed, the execution time will increase.
That's always there. It's the conflict.
There is trade-off.
Yeah, the conflict there
That's
is.
why I am saying if the bag of tasks is there, then there is no benefit of reducing the frequency of the processor.
In fact, bag of tasks are not interesting for scheduling because they don't challenge anything. We rarely do a bag of tasks. Absolutely no challenge. In fact, the name is embarrassingly, what they call it? Embarrassingly parallel jobs. So, yeah, they are not, they're not challenging. They're very easy. Most of the time, your paper is rejected because of this. Because when you schedule bag of tasks, there is no challenge easy. The scheduler will not be scrutinized, right? So try, the reason I gave you 4 different workloads today is before you submit your paper, you want to try mixing it at least with some of these ideas. That way you can show that the algorithm is not only running for a bag of tasks, but it's also handling none of bag of tasks. He's right, bag of tasks, they don't pose anything. You run it on the system. If you lower down the frequency, that means the speed of the processing will lower down, and which basically says it will actually decrease the response time or the total outcome of the entire jobs. But at the same time, they consume a lot of energy. So you need to balance. One idea is actually you move them into very high. Don't change the voltage. Just move it to a smaller number of nodes, and then let them do. When one finishes, let them run on that. So you save energy, but you impact speed. You can't actually work. You can't save energy without impacting the execution time. But the balance has to be there also, right? That is why you work with these two. That's service level agreement violation is where in fact becomes a serious problem, because you want to reduce energy. Nowadays, before, earlier, the servers were very expensive. You want to increase utilization. But nowadays, servers are very cheap. 400,000-500,000 lakh or lakh rupees, you can buy a very nice server. But energy is going up, keep continuing going up. Very, very expensive now in US, in Western countries. So they wanted to exchange that.
So nowadays, game theory is also being applied heavily.
Game
on
theory is applied.
scheduled, resource provisioning.
Game theory is applied. So Pareto equilibrium is used. So, but because most of these things came about of the negotiation, SLA negotiation, and you want to increase utility.
Multi-objective optimization has too much complexity.
Yeah. Yeah.
You have to find out Pareto fronts.
Yeah.
So it also increases the complexity of your scheduling and time also.
Yeah.
So what are the other parameters so that we can reduce the time?
What are the other parameters?
What are the other approaches in comparison to multi-objective optimization?
I don't know. That's a big research question. If I knew, I would tell you. They are huh?
But his question is that the formulation is the multi-objective optimization problem.
Yeah.
Now to handle multi-objective optimization problem, there are multiple approaches. That even though you can apply the Vega and these kind of NSGA2, etc., that they have, people are applying. Even the PSO also is being applied for multi-objective optimization. But he's telling that these are consuming a whole lot of time, let's say, making the scheduling decisions. Then the question is that how we can, let's say, minimize this efficiency of the algorithm, let's say, at that particular level. That is the question.
Now I actually understand. Before I was thinking something else. So, meta heuristics are actually applied. They take long time. But again, the more criteria you use, multi-criteria, the more becomes complicated. So scheduling is already with one objective is already NP hard. And now increasing the number of parameters, it also becomes double, triple, and whatever. So I don't think there is an answer for that because it's already an NP hard problem. But this is a research problem that there are possibilities to improve it. But I don't believe there is a solution because scheduling is already NP hard. If anybody solves that NP hard problem, they will get probably what they call the Nobel Prize or something. Yeah, Turing Award. $1 billion. There you go. Young people, I'm not interested in that area. I will not go for it. Huh?
scientists are more busy thinking about bitcoins nowadays.
Yes, that's true.
Will you be dealing with the cloud security also?
Yeah,
because there are many interested in cloud security.
This lecture?
No, not this lecture, some other
Yeah.
day or something.
Yeah, I am working in that area also, so I'm happy.
So
anybody.
you can give some insight in the cloud security,
Yeah.
so that they can formulate their research problem
Okay.
in this particular area of the security.
Okay, that would be nice. I will do that.
And in fact, you can derive some of the open research problems, so probably they can handle in due course of time.
Yeah. I was actually pushing you into that. I slowly increased. If you see, the complexity of presentation is going up and up. Because I actually came down today a little bit. Yesterday I got 3 or 4 suggestions to explain more what I did yesterday. That's why I went step by step explaining. And I hope that helped and clarified many things. But tomorrow is more. Today we formulate one criteria. Tomorrow we will formulate multiple criteria and show you how hard it is as we go. Okay? We will try.
Actually, in India, the problem is to actually decide what exactly they wish to work.
Okay.
Right? To formulate the research problem. And I hope that the job of the supervisor is just to bring them to this particular track. That actually this is the work that you have to do. Very clear cut, they should have in mind. So most of the even supervisors, they are not, to be very frank, they are not even capable of, let's say, designing the research problem. So let's say if they get some insight that, okay, this is the one I can handle, I can adapt, and which is feasible also, because the research period, PhD research period is not more than 3 to 4 years or so. If they take some problem which is infinitely going high, taking high time, then probably they are, at the end of the day, they are back to square one. So
that's what I actually, in the morning I told you this, this is how you formulate, and I will be happy to show you that, because I know that I have seen what Professor DB said. Many PhD students in Mysore, they have open-ended research problems. They will never finish, never.
This is what the problem is. Because as a PhD student, they must handle some problem which is feasible. And which they can solve in, let's say, 2-3 years, can develop few of the models, let's say 3, 4, 5 models, so that they can compile it and can get a PhD degree.
I have seen a proposal, someone proposing to do fault tolerance, to make the system fault tolerant and make the system deal with real-time data. Then deal with streaming Twitter. There is 6 different areas for one PhD, 6 different very hard problems, and I ask when you're going to finish. But these are not also even linked together. You want to solve one problem and find 4 sub-problems and finish this instead of streaming big data, fixing fault tolerance of the system, and doing something there. One is in India, one is in China, one in Australia, one in US. And I asked him, it is approved? And I was saying, how did you let you do this?
He told him, go ahead.
Yeah, it's impossible. I said impossible. Do you understand where is the fault tolerance and big data streaming come together? Show, even you can't finish big data streaming alone. Why don't you just pick that one and work on it instead of working in 5 different
That is what
areas?
the problem is.
I have seen 7-6 students like that since I came here. That's why this morning I formulated a problem. I showed you this is how you formulate and take it to your supervisor. And I gave you an example, Professor Zahir. He will be happy. I saw him, he was smiling. Because I will be happy if I see something like, clear, this is the problem statement. And you know exactly what I'm solving, exactly what the constraints are. I can help you also with that, because if you come up with something clear, you don't make my head go around, right? If you come with something complicated, as a supervisor, I keep thinking now, what the heck she is trying to do? So now I forget all my jobs trying to help you. But if it's a little bit clearer, then it's easy for me to work with you. I am very much happy to help you formulate a problem. I will show you tomorrow also how you can actually formulate a very clear statement. I know at least 3 people who didn't raise their hands when Professor DP asked, who asked me yesterday, I'm writing my proposal, here it is. But they didn't raise their hands. I know they will come to me later on lunchtime. Don't worry, I'll help you.
There is a very general question. Actually, on one hand, we have grid computing. On the other hand, we have cloud, which is actually dominating the parallel distributed systems world. Cloud is more business oriented, so profit making is involved. Grid, on the other hand, is more for collaborative engineering. So, Professor Rajkumar Goya, as you have, you must have known, actually, has created a cloud over the grid resources in University of Melbourne. So, is grid really dead, or do you really see the future for grid?
Yesterday, I actually got a question that cloud is dead. Cloud has no future. So I think that came from, as I was told, from IIT professor. Is grid dead? There is 2 things, okay? As a researcher, because we actually do research to make it usable by the community. Our research has to be translated into something practical. We just don't do anything like we wanted. Now, from that perspective, cloud is where we actually do have to work. Then there is scientific research also. Grid computing is developed for mostly scientific research, where you can actually send your jobs and run and see how it works. You can experiment with it. But you also know the resources. You know how many nodes are available for you in the other end. Cloud, you don't know anything. You have no clue unless it is private cloud. In public cloud, you don't know anything. So is grid dead? No, grid is not dead. The only difference, major difference, is business model between cloud and grid. And then the other major difference is the management of the resources. Here you may probably get some level of security, some level of quality of service as expected. On the grid, you may or may not get, because it is goodwill, right? Shared in a goodwill manner. It's not cost. And also it can be abused, because you can send a program that is full of error. I have seen this. You send it, it crashes the whole system. But this will not, the cloud will not allow you to do that, because you pay for everything. You become very aware of it. It's a business model. Again, you can't use as a business, you can't actually use your workload on some untrusted systems. And also, if you go for research grant, you can't actually talk about grid, because politicians know now about cloud. So it's catch-2020. You can't actually talk about cloud. This is about grid, because the people who review your grant will say, but Cloud, the grid is actually some 4 or
Gone.
5 years ago is gone.
And I think probably the question was this only. The grid is dead with respect to the research.
Yeah.
Probably.
Yeah. I know what he's, Raj is a good friend of mine. We just, our offices are just, every day we talk basically. He also told me he came here in December and gave workshop, and you told him that I'm coming, and he told me all this. I know what he did, and I know what he's doing. He knows what I'm doing. He knows where I am. I know where he is right now. So, is grid dead? If you ask him, I don't know what he will answer. In fact, did you say he developed on the grid or on cluster?
No, sir, it is on grid.
On grid, huh?
Yeah.
Okay. Yeah, so it's still there. In France, they're using it. In China, they're using it. But they call it cloud. You can call it cloud because cloud, from systems perspective, is a virtualized resources. You can also virtualize your clusters to make it cloud. Do you sell the resources? If you don't sell it, it's goodwill, then you can call it grid, virtualized grid. In fact, we started calling service-oriented grid computing because it is based on services. And then we virtualized it, but all of a sudden, the idea of utility computing came in, the whole thing became cloud.
What he has done there is basically it's a grid, and on top of that we call, a grid is actually a collection of virtual organizations. So what he is doing is, all those virtual organizations he's calling the small clouds. So maybe it's more marketable, or maybe...
Yeah, he calls it multi-cloud.
Yeah.
Multi-cloud.
No, we actually did gateway. The gateway that I actually presented in one of the workshops, if you remember, that is basically what it is. The whole thing is what we actually developed, the gateway. But it helps to be a good businessman or a good convincer to sell whatever you have. It doesn't really matter the quality. So if you are a good talker, good businessman, you can, unless you are technical, and go back and see, show me what is this, what you're doing. I'm not a good businessman. I'm a good researcher. I can't sell anything. I can't even sell myself. And I can't compare with others in that respect. But cloud people, Amazon, Microsoft, they spend a lot of resources and a lot of money. A lot of, they build big data centers and so forth. They have a lot of resources. You can actually call them real cloud computing. But there are also many other companies that say they are also cloud computing. But I have never got time to see which one is cloud, which one is grid. But grid is still there. I know for sure grid is still there because I have colleagues in Europe that they still use this. I have colleagues in India, in China, who still use that. We still also use our data center and still use it. The idea is still there. But we don't take, I don't take anybody for PhD on grid.
Even the applications also, nowadays,
they don't
grid computing, they hardly have any applications.
Yeah, so.
Even in cloud computing now, it's very difficult to find a problem. That we are talking about formalization of the problem, but the problem that how to find the problem, not how to formulate it.
We have
because
a lot
I read more than about 9 months
Hmm.
to find some problems, because even in migration, for example, energy consumption, they are doing well now, but since 2012 it's stable. Only small changes in energy consumption. Then they went after a single data center to distributed data center. Even distributed data center, it's fully explode. Then they went to multi-cloud and federated cloud. But it's very difficult to find problem in cloud because no one is doing in single data center now. It's very difficult to find problem.
Oh, there is a lot of resource provisioning problem in cloud.
Moreover, the fog, the edge computing concept came. You can have the fog integrated cloud. You can have edge integrated cloud sort of thing. And
there is lots of problems in that area. Lots.
And moreover, IoT is also coming. So now IoT is also being integrated in cloud.
Yeah, cloud. Fog computing and edge computing.
See, now, if you look over the research papers, you will find that now they are developing the scheduling algorithm for fog integrated cloud.
Yeah.
So the things are, see, the change is taking place, but the cloud is still, you have a huge lot of problems. Game theory is highly being used in cloud computing nowadays because it is a business model. So game theory is also to be applied there.
Option comes into picture.
Option, bargaining, a lot of things.
Even this, I have one survey about game theory. It's already explored too much. Game theory, I have one.
But none of the cloud service providers applies game theory for resource provisioning, except Amazon, and that too just one instance is spot pricing. That's all.
No, I have one survey. It's only about game theory. They give a survey about 200 papers for game theory only.
It's there, but you see that you do have to develop new and new models. That the game theory is still being explored a lot in cloud provisioning, resource provisioning.
There are lots of open problems in our area in resource provisioning. There is endless problems to be solved, but who has time to solve them? That is the major problem. It's not the lack of.
So far, you did not formulate your research problem.
No, I formulated after 9 months.
So 9 months is okay.
That is small. 9 months is okay for
not yet.
PhDs. People spend 2 years before they can understand even what they're doing themselves. It's normal. If you can't find problems, it doesn't mean that the problem is not there. It is just you when you start. You have these kind of things where you start. You are Superman. After reading 20 papers, you find yourself, I shouldn't study PhD. And then after 3-4 days, or some nice, if you know, family members or nice girlfriend or boyfriend who says wake up in the morning, then all of a sudden again you become Superman or Superwoman, and then goes down. And that takes about 2 years, 1.5 years, 1 year. Then you become, now you cool down. Research means that you slowly read, understand, talk, discuss, ask. So then now you become used to it. You slowly start getting into problem, write your first paper, and then after a month when you come back to it and say, oh my God, I wrote this one. Okay, I wouldn't write this again. You throw it out. You keep going like that. Then you get, after 2 years, you become very good. Because there are some juniors coming in. Now you practice on them. And then you become good and good. You start publishing your first paper, your second paper becomes easier, third paper, okay, then you finish your PhD. This is normal. The first 2 years, a lot of 80-90% of students get confused.
Because when you find a problem, then you read more and more, you find someone solve this problem already, then the difficulty that how you make your problem different. You have to add something to make it. Because I found some problems and I searched, I found someone already solved it. Then how to add something to make it different?
You don't add something to make it different. You just make it different. Don't think that research problem is not like a husband and wife. No. They come in a different flavors. So it is just you. You see, if I take now storage, a lot of work in energy is done in processors, in CPUs, right? But it's not only CPU, there is storage, there is network, okay? So you can explore this. There is connection between them. You read a paper, they talk about CPU, how to reduce the consumption of energy by CPU. CPU is one element. In the whole schema of things, there are so many things. Application itself, bad applications take a lot of energy. Middlewares take a lot of energy. Okay? So if you explore, sit down and say, yes, there is a wife and husband, but there is also something in between here. Mother-in-law,